Good day everyone, and welcome to our presentation. Today, we delve into the fascinating world of scientific language models with our paper, Galactica, a large language model for science. We explore how these models, specifically Galactica, can disrupt traditional methods of accessing scientific knowledge, absorb technical information, and bridge the gap between scientific modalities and natural language. Prepare to be intrigued as we discuss the potential of language models to revolutionize our interaction with knowledge. Let's get started. The traditional method of accessing scientific knowledge has been identified as a bottleneck. It heavily relies on human effort, leading to significant issues with knowledge throughput. We propose a shift from this paradigm, suggesting the use of language models as a new tool for exploring literature and scientific knowledge. This aims to reduce human effort and increase efficiency. Language models have shown to be effective absorbers of technical knowledge, including LaTeX equations and chemical reactions. They can compose a curated knowledge base for knowledge-intensive question-answering tasks. This demonstrates the potential of language models to revolutionize how we access and process scientific knowledge. Our exploration of large language models, or LLMs, has revealed their potential as a bridge between scientific modalities and natural language. This is a significant stride forward in the realm of scientific knowledge processing. We've seen promising results in a variety of tasks. For instance, LLMs have shown proficiency in IUPAC naming, a fundamental aspect of chemical nomenclature. They've also demonstrated their potential in drug discovery tasks within the MoleculeNet framework, formulating these tasks in a natural language prompt and achieving strong results without direct fine-tuning. Furthermore, we've seen the potential of LLMs in automatic protein annotation, a task crucial to understanding protein function and structure. These findings underscore the transformative potential of LLMs in the scientific domain. Let's consider the illustration on the left. It depicts a human using internal or external working memory to solve a task, such as calculating the average of a set of numbers. This is a metaphor for how language models can absorb and organize large amounts of technical knowledge, mirroring human cognitive processes. Now, let's turn our attention to the traditional method of accessing scientific knowledge. It primarily relies on a store and retrieve paradigm. While this method has served us for over half a century, it has its limitations. The most significant of these is that the reasoning, combining, and organization of information still require heavy human effort. This leads to what we call a knowledge throughput bottleneck, where the rate at which we can process and understand information is limited. In our research, we explore how language models might disrupt this paradigm and offer a new, more efficient way for humanity to interface with knowledge. Our proposed solution is to leverage language models as a new interface for knowledge interaction. This approach disrupts the traditional paradigm, reducing the human effort required in reasoning and organizing information. The motivation behind this approach is to address the knowledge throughput bottleneck and to explore the potential of language models to take on tasks that are currently human specialisms. This could revolutionize how we access and interact with scientific knowledge. However, previous attempts have been limited by the store and retrieve paradigm, which lacks the ability to absorb and organize large amounts of technical knowledge. Our work aims to overcome these limitations, and we'll delve into how we've done this in the following slides. Our research proposes a novel approach to accessing scientific knowledge, leveraging the power of language models. These models serve as a tool for exploring literature and scientific knowledge, absorbing technical knowledge such as LaTeX equations and chemical reactions. They can also compose a curated knowledge base, performing well in knowledge-intensive tasks. We also delve into the potential of large language models, or LLMs. These models can act as a bridge between scientific modalities and natural language, offering a fresh perspective on addressing the knowledge throughput bottleneck. This innovative approach could revolutionize how we interact with and utilize scientific knowledge. Our research proposes a new approach to exploring scientific knowledge using language models. These models are not only capable of absorbing technical knowledge, such as LaTeX equations and chemical reactions, but they can also compose a curated knowledge base. This opens up a new way of bridging scientific modalities and natural language. We're moving away from the traditional store and retrieve paradigm. Instead, we're leveraging the power of language models to absorb and process complex technical knowledge. This shift has the potential to revolutionize how we access and interact with scientific information. Our research has shown that language models can effectively compose a curated knowledge base, performing exceptionally well in knowledge-intensive tasks. We've utilized a working memory token approach, which has shown strong performance on mathematical benchmarks, such as MMLU and math. But our work doesn't stop there. We've also been exploring the potential of large language models, or LLMs, to bridge the gap between scientific modalities and natural language. This includes tasks like IUPAC naming, drug discovery tasks like MoleculeNet, and even automatic protein annotation. These initial investigations show promising results, indicating that LLMs could be a powerful tool in the scientific community. In essence, our work is pushing the boundaries of what language models can do, opening up new possibilities for knowledge absorption and scientific exploration. Our research introduces the use of Galactica, a model that learns tasks such as IUPAC naming through self-supervision, showcasing the adaptability of language models. We've also formulated drug discovery tasks like MoleculeNet in natural language, achieving strong results without direct fine-tuning. We've explored the potential for automatic protein annotation, further demonstrating the versatility of language models in scientific tasks. Our evaluation of results shows that language models outperform retrieval pipelines for citation prediction, underlining the effectiveness of our proposed method. In essence, we're leveraging the power of language models like Galactica to tackle complex scientific tasks, from drug discovery to protein annotation, with promising results. Let's delve into the key results of our research. We've discovered that language models are capable of absorbing technical knowledge, including LaTeX equations and chemical reactions. This is a significant leap forward in the field. Moreover, these models have shown to outperform retrieval pipelines in citation prediction tasks, demonstrating their potential in the realm of academic research. They can also compose a curated knowledge base, excelling in knowledge-intensive question-answering tasks. Our research also highlights the strong performance of language models on mathematical MMLU and math benchmarks. This suggests that these models could be a valuable tool in the field of mathematics. Lastly, we found that large language models, or LLMs, show potential as a bridge between scientific modalities and natural language. This could revolutionize the way we approach scientific research and discovery. The figure on the left illustrates Galactica's attention to functional groups, further emphasizing the potential of these models in scientific research. Our research has led us to some key contributions. We've developed a novel approach to accessing scientific knowledge using language models, which have shown an impressive ability to absorb technical knowledge, such as LaTeX equations and chemical reactions. These models can also compose a curated knowledge base, proving invaluable for knowledge-intensive tasks. We've also explored the potential of large language models, or LLMs, to bridge the gap between scientific modalities and natural language. The figure here illustrates how Galactica's citation distribution becomes closer to the ground truth as the model scales. This is evidenced by a decreasing KS distance with scale and an increase in histogram overlap, indicating that language models can outperform tuned sparse and dense retrieval pipelines for citation prediction tasks. In essence, our work has demonstrated the strong potential of language models in the realm of scientific knowledge access and understanding.